Hello everyone and welcome to the CS194 course, Introduction to Digital Design. This is our first lecture, which basically covers and provides some information about how we are going to proceed with the course and gives you some introduction about the basic concept in digital design. My name is Farshad Mashhadi and this is my email address. You can reach me anytime with your questions and your concerns. So in this course, we're gonna learn how computers represent information, how actually computers perform basic and advanced arithmetic operations and computations, and we're gonna understand how hardware and software interact and work with each other. So the course is going to be fully remote, both the lectures and the labs. I'm gonna upload these slides on the Blackboard, and you can have access to the video recorded files on the provided YouTube channels. We're gonna have office hours from 4:30 to 5:30 p.m. On Tuesdays and Thursdays on the provided Zoom channel, and you can send me your questions and if you have any concerns about the course to my email address. I'm going to be more responsive over the weekend, but I try to be quick as much as possible. Homework is posted on Thursdays and will be due on Mondays by midnight, and it is going to be using online submission. The instructions on how to perform the labs will be shared with you guys soon. A 20% per day penalty will be applied for late submissions, and we're not going to accept submissions later than 5 days. We're going to have makeup exams for those who have missed their exams, but they have to have a good reason or genuine reason of why they have missed those exams. And it is applied, it's the same rule applied for homeworks too. So the grading will be 10% for homework, 10% for lab assignments, 25% for exam 1, 25% for exam 2, and 30% for exam 3. So let's begin. Digital computers or digital systems are used in many scientific and industrial applications, and some of the examples of them are like digital telephones, digital cameras, electronic calculators, laptops, and so many other electronic devices that you have interaction with in your daily life. One characteristic of digital system is their ability to represent and manipulate discrete elements of information. So what is discrete? Any set of numbers that is restricted to a finite number uh, contains discrete information and is called discrete number. Examples of discrete sets are the 10 decimal digits, the 26 letters of alphabet, or the 52 playing cards, or like 64 squares of a chessboard. So discrete elements of information are represented in digital system by physical quantities. Uh, which we call signal. Electrical signals such as voltage and current are the most common. The signals of the most of the digital systems use just two discrete values and that are therefore said to be binary. A binary digit which is called a bit has two values, 0 and 1. There are other forms to represent those binary values, and one of them is 0 and 1, the other one is false or true, or the other one is low and high. And we also can say off and on. Binary values are represented by values or ranges of values of physical quantities. So in order to get more familiar with digital system, we have to know that digital system is an interconnection of digital modules. To understand more the operation of each digital module, we have to have basic knowledge of digital circuits and their logical function. Uh, a major trend in digital design is the use of a language called HDL to describe and simulate the functionality of a digital circuit. Uh, HDL resembles a programming language and is suitable for describing digital circuits in a textual and more understandable form. It is very important for us to become familiar with the HDL-based design methodology to learn more about how digital system is actually working. So as we mentioned in previous slide, digital systems manipulate discrete quantities of information that are represented in binary form. Digital circuits also are referred as logic circuits, process data by means of binary logic elements or logic gates using the binary signals. So the purpose of this chapter is to introduce the various binary concepts as a frame of reference for further study in the succeeding chapters. A decimal number such as 7,392 represent a quantity equal to 7,000 plus 300 plus 9 tens plus 2 units. To be more exact, we can show it this way. In general, a number with a decimal point is represented by a series of coefficients. And to be more general, a number expressed in a base R system has coefficients multiplied by the power of R. So the decimal number system is said to be of base or radix 10 because it uses 10 digits and the coefficients in this system are multiplied by the power of 10. On the other hand, in the binary system, we have only two possible values, 0 and 1. In order to convert numbers to be represented in decimal system, we will multiply the coefficient by a power of the radix, for example, 2 power of j, and we add them together to obtain the decimal equivalent of the number. For example, in order to convert a binary number of base which has the base 2 to a decimal value, we know that R is equal to, so 2 minus 1 is 1, so ranges are 0 as 1 as we have mentioned. So we'll start by numbering these binary values from right to left. So we have 5 binary on the left side, and starting from the left, we multiply 1 by 2 power of 4 added by 1, the second binary value, multiplied by 2 power of 3. 3 comes from here, added to 0, multiplied by 2 power of 2, and then 1 multiplied by 2 power of 1 added to 0 multiplied by 2 power of 0. And then, because we have fraction numbers, we're gonna start numbering this way. So we have minus -1 and -2. So we're gonna keep adding 1 multiplied by 2 power of -1 or -1 added to 1, another one we had here, multiplied by 2 power of -2. And if we add and if we do this summation, we're going to find that the decimal representation is 26.75 in terms of base 10 or decimal values. Another example is showing how we can convert numbers from base 5 to decimal values. So we're going to have 0, 1, 2, 3. And here we have -1. So we multiply 4 by 5 because numbers of base of 5. Power of 3, 0 multiplied by 5 power of 2, 2 multiplied by 5 power of 1, and then 2, and then 1 multiplied by 5 power of 0, and then 2 multiplied by 5 power of -1. And if we do this summation, we're going to find that the decimal representation of this number is 511.5. There's another example you guys can try in order to get more familiar how you can convert numbers from different bases or octal base to decimal values. So here is another example to convert a base 2 number, a binary number, to decimal value. So we start numbering from here, 5. So we have 1 multiplied 5 power of, 1 multiplied by 2 power of 5 added to 1 multiplied by 2 power of 4, and so on, which gives us the value of 53 in decimal values. So we may encounter some big numbers. Maybe if the binary value is too large, we have to do some, we may have some high value powers like 2 power of 10 or 2 power of 20, and we may not be able to calculate them. By hand, we may need a calculator, or for that purpose we have a table which you can use in your calculations. In next slide you're gonna see it. So this table is going to help you a lot in your calculation. You can memorize some of them, and you may already know that, okay, 2 power of 1, 2 power of 0 is 1, 2 power of 1 is 2, and 2 power of 15 is 32,768. And this is gonna help you a lot with your calculation. And there are some values which helps you a lot if you keep memorizing them until you know them by heart. And these are the values. And you're gonna learn them anyway. For just a quick recap, there are 4 major base systems, number systems. Those are binary, octal, decimal, and hexadecimal. And the radix are 2, 8, 10, and 16. So we know that the range of the values they get could be found by this equation. So for binary 0 and 1, octal is 0 to 7, decimal 0 to 9, and for hexadecimal it's 0 to 9. And then for showing the remaining values, we have A, which is equivalent to 10, B equivalent to 11, C 12, D 13, E 14, and F 15. So far we have learned how we can convert numbers from base R to decimal values. But let's see how we can do these vice versa, or convert from decimal to to numbers with different bases. This example, we want to convert 41 to binary, which has radix or which is of base of 2. So we divide 41 by 2, we get integer quotient 20, and our remainder is 0.5, which is not 0. Because it's not 0, our first coefficient is 1. We divide 20, which is the result, by 2, we get 10, our remainder is 0. So the coefficient will be 0. We divide 10 by 2, we get 5, remainder 0, and then coefficient will be 0. And we keep doing it until our integer quotient becomes 0. And then we start from the last coefficient we get, and we find our binary conversion. So starting from here, we get 1, 0, 1, 0, 0, 1. So the conversion of converting 41 from decimal to binary gives us this value. We can try finding we can try converting numbers from decimal to numbers from different bases using the same approach. But we know that the value here is related to our radix we want to convert to. Now let's look at another example to see how we can convert decimal values to octal values, or numbers with base of 8. So the number is 153. So dividing 153 by 8, which is radix of an octal value, we get 19 as the quotient, and remainder will be 1. Dividing 19 by 8, we get quotient of 2, and remainder will be 3. Dividing 2 by 8 gives us quotient of 0, and remainder is 2. And if we write the values of remainder from this order, we get 2, 3, 1, which is our result. Now let's see how we can convert a decimal fraction value to a binary value. So the number is 0.6875. So to do that, we multiply that number by 2, which is the radix of binary value. We remember that r was equal to 2 for binary value. So the answer of the first step is 1.3750. The integer value, we write it here, and the fraction is 3750. So the first coefficient is 1. Second step, we multiply the fraction by 2, and the answer is 0.75. The integer is 0, and the fraction is 0.75. Second coefficient is 0. We continue the same process until our fraction becomes 0, and then we write 0.1011 in the base of 2. I put here another example of converting a decimal fraction value to an octal value for you guys. I suggest you to do this on your own to get more familiar with the process. The arithmetic operations in binary systems more or less follow the same as what we have in decimal numbers. I'm going to give you some example on how to do them. In order to do addition in binary systems, we start from the right column. So adding 1 and 1 gives us 1, 0. So 0 stays here. The additional 1 which we have, which we call it carry bit, goes to the second column. Adding 1, 0, and 1 gives us another 10. So we keep 0 here, an additional 1 goes to third column. Adding 1 and 1 gives us 1, 0, and then adding another 1 here gives us 1, 1. This one stays here, and the additional or carry bit goes to the fourth column. Adding 1 and 1 and 0 gives us 10. 0 stays here, and the additional 1 goes to the fifth column. And adding 1, 0, and 0 gives us 1. And in the end, adding these two numbers in the last column gives us 1, 0. And this is how we can do the addition. How we can do the subtraction. To do the subtraction, we start again from the right column. Subtracting 1 from 1 gives us 0. In the second column, 0 minus 1 gives us 1. But we have to borrow a bit from the higher order column, which is this column, the third column. So this one becomes 0. Subtracting 1 from 0, 0 from 1, again gives us 1. And then the third column, the fourth column becomes 0. Subtracting 0 from 0 gives us 0. Again, 0 from 0 gives us 0, and 1, negative 1, gives us 0. And this is how we do the subtraction. In the end, I'm going to show you how we can do the multiplication. So we're going to multiply these two numbers together. So starting from the right number, and this is also following the same rules as decimal values. So we start from this bit. So multiplying 1 by 1, 0, 1, 1 gives us this value, the same value. Then we multiply the second bit to the 1, 0, 1, 1, and it gives us 0, 0, 0, 0.
And in the end, multiplying 1 by 1, 0, 1, 1 gives us 1, 0, 1, 1. And if we add them together, this gives us 1, this gives us 1, this gives us 1, and also 1 and 1 again gives us 10. 0 stays here, and the additional carry bit comes here. Added to 0 and 0 gives us 1, and then the last bit is 1, which we write it here. And this is how we do the multiplication in binary systems. In digital computer and digital system design, it's really important that we know how to convert from a binary value to octal and hexadecimal, because the shorter patterns of hex characters are easier to recognize than long patterns of 0 and 1s. In this table, the first 16 numbers in the decimal, binary, octal, and hexadecimal is shown, which we can use later. But in the next slide, I'm going to tell you how we can convert from binary value to octal and hexadecimal. So let's see how we can convert numbers from binary to octal and hexadecimal. To convert from binary to octal, we should position the binary numbers into a group of 3 digits and start from the left, from the binary point, and go to the left and to the right. So for this example, we start from the binary point and we group the binary values in groups of 3 to the left and to the right. So the first value is 3. How did we come up with that? It's 0 multiplied by 2, power of 2. So the answer is 3. This is how we can come up with the other numbers too. And this is the octal representation of this binary value. For converting to hexadecimal, we follow the same procedure. We start grouping from the binary point, but we group them into digits of 4. Okay, so we have 6 groups. The first one is this group, how we can convert this to hexadecimal. We have 1, 2 power of 3, 0, 2 power of 2, 1, 2 power of 1, and the last digit, 2 power of 0. So this is 11. If you look at the previous table, the table in previous slide, 11 is equivalent to B in the hexadecimal form. Same thing, we come up with 6. C is equivalent to 12 in hexadecimal form. And this is the hexadecimal representation of this binary value. So let's see how we can convert from octal to hex or to hexadecimal or to binary. So 6, we can show 6 in binary form using 1, 1, 0. 7 is 1, 1, 1. Because it is octal, we should group them in 3 binary value. And this one shows 3 binary point. 0, 0, 1 represents 1. 0, 1, 2. And 1, 0, 0 represents 124. And this is how we can find the binary form of an octal value. For a hexadecimal, we know that we should find binary values with group of 4. We have our binary point. D is equivalent to 13. So this one, if we convert this we have 1 to the power of 3, 1 to the power of 2, 0 to the power of 1, and 1 to the power of 0. This is equal to 13. If you look at the previous table, 13 is equivalent to D. So this is how we come up with the binary value 6. This is how we can show 6. 0 is 4 binary digits of 0, and this one is 3. This is now the end of our first lecture. On next class, we're going to continue on number systems and number codes.